Welcome to our last lecture on energy in the IoT. So, today's topic is intermittent computing. So, intermittent computing is something that is special to IoT systems because most of the systems that use energy harvesting are actually used in IoT contexts. So, in the energy harvesting systems, we very often have the case that the availability of energy is quite sporadic and unreliable. So, of course, if we don't know how much energy is available and when the next energy will be available, our software has to be able to cope with this. So we need to ask ourselves the question, like, how can we handle this unreliable availability of energy when we use energy harvesting for our system? So, with energy harvesting, there are often only short amounts of runtime between long periods of recharging. And you see this in the diagram on the right-hand side. So, time is on the x-axis. The amount of energy that could be harvested is shown on the y-axis, and this harvesting could be everything we've discussed in the first lecture of energy, like a solar cell, for example. So you see it takes quite a long time to harvest an amount of energy that's sufficient to run the CPU. And then the blue shaded times are actually the times where your CPU, your processor, is running and where it can actually compute things. And then, of course, as soon as you start computing things, the amount of energy you have available goes down until it reaches a point where, it just needs to shut down the system because you need more energy in order to hopefully continue operating your system. So essentially, you have two thresholds here. You have an on threshold, which means this is the energy available that enables you to turn your device on. And then as you deplete your energy storage again, then you have to turn your device off at a certain off threshold, or depending on the voltage going down, for example, in a capacitor, the device will actually turn off automatically because very many embedded chips, like embedded systems on chips, have what we call brownout detection, so they automatically initiate a shutdown of some kind. If the supply voltage goes below a certain value. Now, the problem is if you continuously turn off your machine and then turn it on again and turn it off and turn it on, then usually your processor would just start from the beginning, so from the very first instruction. So you would execute your program over and over again, and this would mean you would have to write a program that runs so fast, so that needs so little time, that it's actually able to complete its operation in this short amount of time that's actually available for computing. Now, while there might be application use cases where this is feasible, this is not really great for the general case. So what we would want is we want to split the execution of our program over these phases in which energy is available. And in order to do this, we need to save certain state of the application in between the compute phases. So during the phases where no energy is actually available, where our system is not running. And the question is, how can we actually achieve this? How can we support applications in doing this? Now, the approach, is actually called intermittent computing because we compute only when enough energy is available, and we turn off the device in all the other phases without sufficient power or energy. And the important thing here is really to guarantee progress in the computation. So we don't only always start at the beginning, but we can continue where we left off the last time when we lost power. So IoT devices we've seen harvest energy, but harvesting energy itself is not enough because usually when the times when you harvest energy are not exactly the times when you actually need this energy. So harvesting energy and then using it to directly supply your processor or your complete IoT system is not the common case. There are a number of reasons for this. So the one reason is that usually you need the energy at different times than when it's harvested. That's a typical example of a solar-powered street lamp. As long as the sun is shining, You can collect energy from the sun using a solar cell, but you don't need to turn on your lamp. And if it's dark, you can obviously not collect energy from the sun, but you would need to turn the lights on in order for people to see something. So essentially, we would need a way to store the energy in between, well, the time it's collected and the time it's used. Now, there are also several physical reasons for not directly powering a device from an intermittent energy source, and this might be mostly related to the voltage and current supply characteristics of a semiconductor chip. So very often the voltage and the current supplied by an energy harvesting device are not really directly compatible with what our semiconductor needs. So a storage element in between, like a capacitor, as we've seen, or a small battery, can help to alleviate these differences by adapting the voltage and the current as needed. So IoT devices harvest energy and they also buffer this energy as long as it's available, and then use this buffered energy to operate when sufficient energy is stored, for example, in our capacitor. And we see a very little IoT node here on the right hand side of this photo. So you see this long piece of PCB. This is actually a battery, and the length of this battery is adapted to be exactly the wavelengths of one of the typical radio frequencies that are used, for example, in radio transmission, so Wi-Fi at 2.4 or 5 gigahertz, or one of the GSM radio frequencies we've seen in the networking chapter. And then, of course, when a radio wave comes in, it causes electrons to move along this piece of PCB, which acts as an antenna because it has exactly the right length to match the frequency of this radio signal. And then when electrons move, you have a current. And if you have a current, then of course you can collect energy somehow. So we've already seen operations in these devices are called intermittent because the energy is not always available to harvest. So we have phases with no energy where we need to harvest energy, and we have phases where we can use the harvest's energy. And since we cannot predict how much energy we're going to harvest in the future, we actually need this buffering because we would need to buffer enough energy to at least do some useful amount of work, which takes some time, both the buffering of the energy and doing the useful amount of work. So this is very different to your typical program. So your typical program is written with the idea that it runs to completion unless you turn your computer off or it crashes or something. So the key distinction between conventional execution of programs and intermittent execution is that a conventionally executing program is assumed to run to completion, but an intermittent execution of a program must be able to span power failures in order to eventually complete its execution, so to fulfill its intended task. So what is the consequence of using intermittent computing or having to use an intermittent operation in your device? Now, first, it makes the control flow unpredictable because, well, you turn off your machine and when energy is available, where do you end up? Second, if you always have to start from scratch from the beginning, then, well, turning off power and turning it on again later compromises an application's forward progress because you're doing the same things at the beginning of your program over and over again. It can leave memory inconsistent, and it can also leave devices inconsistent with its environment. And it can also complicate device-to-device communication because you cannot receive a packet over radio or some other network when you don't apply power to your radio at that moment. And in very many applications, you can actually have power failures that can occur like hundreds of times per second. And to tolerate such modes of power failure, you need to adapt a system on multiple layers. So you need to introduce something we call an intermittence-aware design, and this affects programming languages, this affects the runtime you use, and maybe also the application logic you use. So let's go into some details of the problems or the challenges that are arising due to the use of intermittent computing. We've seen control flow before, so if a program is executing and then a power failure happens and then you resume the execution of your program after a power failure, this is what we call a discontinuity in the control flow. And we cannot express this in our usual programming languages. So it's not explicitly expressed in the source code. We cannot know when it is going to happen because this depends on the amount of energy available. So this is a bit like an interrupt where we also have to save state and restore it. But it's even worse because we don't have the power maybe to save state. So for control flow, IoT programmers must deal with implicit control flows to to possibly unpredictable points in the execution history of a program. So maybe you have to go backwards a bit in your program to a recent checkpoint or to a beginning of a task. And this is something your software usually doesn't expect. The second point is data consistency. You can use checkpointing to store the current state of a system, and then when after taking a checkpoint the power goes off, you can actually restore this checkpoint, and this consists of all the data in the most naive case, all the data in your system, and then you can continue running from there. So a naive combination of checkpointing and direct access to what we'll see in a minute, non-volatile memory, which is able to retain data across power failures. If you do this on an intermittent device, then you can actually have memory inconsistencies due to this repeated execution of code that comes after the checkpoint. The third point here is what we call environmental consistency. So uh, often you have sensors receiving inputs from the outside, and if you run those sensors on an intermittent computing device, you might end up with a very old, what we call stale sensor value, because that might be the sensor value you've checkpointed, well, some seconds ago when there was power available, but now in the next phase with available power again, this old sensor value doesn't make sense anymore, or it just confuses the system because it might be fusioned, so combined with other current sensor readings and give false information. So this is the sensor problem here that we've seen already, that it would make sense to timestamp data from sensors in order to figure out if the value of the sensor is actually still useful. And finally, we have concurrency. So sensors, peripheral devices, and collections of microcontrollers may all operate concurrently as a single intermittent device, but they could also operate independently. So we might have different power supplies for sensors and from the CPU. And if these run intermittently, for example, our device drivers would have to be adapted to work with the non-availability of a device at runtime. Finally, this is not mentioned on the slide, but of course important in a distributed wireless system. If there's no power, you cannot receive any packets, so you might run into the situation where you actually don't receive information from your communication partners because it's always sent by coincidence in the phases where you don't have enough power to receive them. So what can we do to solve this? So very early systems had a mode which we call fail and restart. Fail and restart means when we run out of power and well, then power becomes available again, the CPU is reset and our execution of our program starts from the beginning until power is lost again. So this means we can only run for very short times. Our program has to be completed in a very short amount of time. That's not what we want. We want to ensure the progress so that every time that a bit of energy is available, our program can actually continue in its execution and get to a point further down in its execution. And while doing this, we need to ensure the correctness of the programs. So we still need to ensure that the correct results are calculated. And there are two common techniques used for ensuring progress and correctness in intermittent computing IoT applications. One is called checkpointing. So checkpointing means, as I've already mentioned, that we take regular copies of the complete consistent state of a program at a certain point in the execution of the program, store it somewhere safe in non-volatile memory, and then when power is lost after a checkpoint is taken, then we can restore this information. We lose only a bit of computation, and we can continue where the last checkpoint left us. So very often you have general checkpoints that checkpoint everything in the system, which are interleaved in the code of your program. So you identify certain program points where you actually call a checkpoint, and this checkpoint copies all of your variables out into non-volatile memory. So before power off, your state is saved, and then at power on, you still run into reset, but your reset handler then checks if there is a checkpoint in memory, and if there is a checkpoint, it doesn't start from scratch, but restores all the data, the current program counter, stack contents, and so on, and then continues running from there. The other option to solve the intermittent computing problem is task-based. So here we divide the computation that takes place into separate tasks which do, well, independent smaller units of computation. And the internal state of a task is thrown away at power off. So if a task, a small one, does not run to completion, well, it has to be re-executed. So we need something with what we call a transactional semantic. So either a task executes completely to its end and writes out its result, or a task is interrupted while it's running. And if this happens, then it is not allowed to persist any changes, so we have to run it from scratch. And then the tasks we needed are always restarted from scratch at power on. So it depends on your software architecture and on the, essentially application you want to implement, if one or the other model is more suitable for your use case here. So as we've seen, intermittent computing requires some sort of what we call non-volatile memory. Because when power is lost, not only your CPU stops running, but all information in what we call volatile memory, so usually RAM, is lost. Because a RAM needs power to actually keep its contents alive. So the software running on an intermittently operating device executes until energy is depleted. The device detects this brownout, usually by checking the supply voltage, and if it's below a certain threshold, then it shuts off. And when energy is available again, then software resumes execution, usually from some point in the history of its execution, and that might be the reset or beginning of main or a checkpoint. So this checkpoint needs to be retained until power is available again. So we need to make sure that this checkpoint data is not lost. So we need to store it somewhere in non-volatile memory before power loss. Of course, saving a checkpoint, this can be quite an amount of data, takes time and energy itself. So we need to really make sure that we save a checkpoint, just so that we have enough time so that the complete checkpoint can be saved before power is lost. If we just lose power in the middle of writing a checkpoint, then we have like half a checkpoint written, and then if we try to restore that checkpoint from scratch, that will end in disaster, obviously. So a checkpoint, if it's written completely and correctly, enables our software to continue at the point it was stopped due to the power loss, and this stores all the runtime data, so usually in a microcontroller it's processor registers, the stack contents, and the heap contents. Now where's your program actually stored in microcontroller? So the program is usually stored in flash memory. Flash memory is non-volatile memory, so flash memory retains its values when it's powered off. So we don't need to take care of saving the program unless we have something like a just-in-time compiler or similar where we generate code at runtime. But let's just assume we're not going into such complex systems. And so essentially, we just need the runtime state of your program to figure out where it was executing and which context it was executing in. Yeah, so intermittent computing itself using checkpointing can cause a number of problems here. So on the left-hand side at part A, you see a problem that occurs when the amount of time that passes between two backup points, shown in green on the left-hand side, is just too long. So you take a backup, which creates a checkpoint, and then you run some code additionally after the backup. So you do some sensing and some processing, but it takes quite a lot of time. So when you restart after this power failure that's indicated using the red line, you have to go back to the first backup because you never reached the second backup. And then, of course, you also have very little energy, so you can do a bit of sensing and processing, but then you have a power failure again. So this means you end up again after your first backup. So you do the sensing again, though the processing, but you never really make any progress unless you would have a phase with very much energy available, which depends on your application or on sheer luck. So this means that when you do checkpoints, you need to do them regular enough to actually make sense. But if you do checkpoints too often, then you waste most of your processing time and your energy on doing checkpointing instead of just achieving progress in your program. So that's again an optimization problem. A second problem might occur, as shown on the right-hand side, when data consistency is questionable because you have non-volatile memory, and this non-volatile memory actually is used also after a backup. So we have another program on the left-hand side for program 2 with 2 backup points, and this is running a loop. So this is just running a loop, calculating the result by summing all of the elements of an array. Now, after the first execution of program 2, well, you have a sum S stored in result. And note that result was set to 0 before the backup, but it's now in non-volatile memory. So when you execute this again, this loop after the backup, then you add up more values to result because it's no longer reset to 0. So you might end up in 2 times S, and in the nth try, you might end up in n times S. So you get an incorrect value out of this behavior of computation. So just using checkpointing without thinking about it really results in problems in your execution of your IT programs. So you need to invest quite a bit more work into getting it to work correctly. So let's quickly talk about memory in IoT nodes. We've already talked about volatile and non-volatile memory. So as the name says, volatile memory loses its states when power fails, so it loses its contents. So that does not necessarily mean it's all reset to 0. Especially DRAMs are reset to some random pattern after they get power again. So that's why you need to run a memory test and clear the memory usually when you power up a computer or after reset. So we've already seen different kinds of RAMs. So SRAMs are what we call static RAMs. So they're relatively small, they're relatively expensive, and they're relatively low on energy consumption. And they're often used for caches, scratch-fed memories, as we've seen in the previous lecture, or used as in general the RAM of a microcontroller, which is on chip. It's fast, it's energy efficient, but it takes a lot of space on your chip and is relatively expensive to manufacture. So you usually only have very little amounts of SRAM, so a couple of kilobytes or a couple of dozens of kilobytes on your chip. If you need larger memories, like main memories, in more complex systems like a Raspberry Pi or your notebook, you usually use dynamic RAMs, DRAM, and these dynamic RAMs store information in capacitors, and this information stored in a capacitor is slowly leaking away because the capacitor is losing its charge, so it has to be refreshed regularly. So DRAMs are quite more cost effective, but they are less energy effective, and they're also less predictable because you have to run this refresh cycle all the time in order to keep the information consistent in your RAM. So SRAM is not only used for RAM, but also for caches, and usually also for implementing the registers in the CPU. No matter which type of RAM you're using here, SRAM or DRAM, both lose their data when power is lost. In contrast to this, we have the non-volatile memory, so this retains its state on power failure. And of course, you're using some of this every day in your USB sticks or SD cards. So these, or SSDs obviously, so these usually use a sort of flash memory called NAND flash. So flash memory is a memory where storage is actually, pushed into a level that it cannot, where energy is pushed or electrons are pushed into a internal level or state, that it cannot leave on its own. So essentially, that would mean flash can retain data for quite a long time, not indefinitely, but many years at least. So these are very useful for permanent storage of data, so replacing floppy disks, hard disks, and so on. So nobody uses floppy disks today anymore, I guess. Many people don't use real hard disks, physical hard disks anymore, magnetic hard disks. So these have all been replaced by this NAND flash technology in SD cards, in USB sticks, in SSDs. Now the problem with NAND flash is it's large and it's relatively cheap, which is nice, but you can only read, write, and erase it in blocks. For example, 512 bytes at a time. So if you just want to change a single byte in such a NAND flash, then you have to read the block, you have to change that single byte, and then you have to erase that block, and then you have to write the block's contents back. And you can imagine this is quite a bit of overhead. And in addition, doing this very many times means you wear out the flash. So all flash memory is constrained to a number of rewrite cycles. So you can only rewrite a block a certain amount of time, depending on the specific manufacturer and specific technology used. So this might differ between 10,000 times and maybe 10 million times. So this is why SSDs also have this maximum amount of data you can write to them, like whatever you can write like 10 terabytes to a small SSD, because that would mean that after 10 terabytes, even if you distribute your writes evenly over all of the blocks available, which is called wear leveling, that means after 10 terabytes, all of the guaranteed write cycles for all of the blocks of your SSD would be used up. And then you should take a copy of the SSD as long as you can read it. You need to throw it away and buy a new one. Another sort of flash memory is what we call NOR flash. So NOR flash is usually very small, but it has the advantage that you can erase and rewrite every single byte. So this is much more convenient when you don't store your data in blocks, like on a file system, on a disk, or on an SD card, but when you want to store data, for example, like a variable used by a program. There's an older technology of non-volatile memory called EPROMs. So EPROMs were essentially chips with a quartz glass window so that you could apply light to the transistors, storing your information on that chip. And if you used high energy ultraviolet light, you could actually kick the electrons out and erase that again. Now, this took a long time, and this was a very specific technology. And a couple of years later, engineers actually developed an electrically erasable, programmable read-only memory. That's what PROM stands for. So this is also byte erasable and writable, but still it's relatively slow, it's relatively expensive, and it's very often replaced by flash memory today. A more recent development is what we call FRAM. So this is a ferroelectric RAM, which uses ferroelectric effects, so essentially electromagnetism, to store 0 and 1 bits. If you know a bit about computer history, you might know that the very first computers in existence also used something with magnetism. So they actually used ferromagnetic storage or core memory storage, where essentially very little pieces of magnetic material, essentially just donuts that have like a millimeter in diameter in the most recent forms. And these are made of magnetic material that you can magnetize in one or the other direction, depending on which direction the current flows through the middle of this donut. And so this can store a bit, like either where magnetization is clockwise or it's counterclockwise, so it's a 0 or a 1. So while these sound similar, so you have magnetic technology in this core memory from the 1950s and 1960s in the very first computers, and you have this FRAM, ferroelectric RAM here, they are based on different applications of magnetism. So essentially, while this sounds similar and they work pretty similar, they're completely different technologies. So you don't have little ferromagnetic cores on your chip. It's just semiconductor technology as usual. And finally, there's another way to achieve non-volatile memory. And this makes use of the fact that SRAM doesn't need refresh, so you don't need to run refresh cycles all the time, and that is relatively low on energy consumption. So this means you can actually attach a a backup battery to an SRAM chip and then preserve the contents of the SRAM as long as no other energy is available. This is very often done for very small SRAMs, for example, in units in chips that also include a timer for keeping real-time information, and then this also contains information about additional current data, like the current date or additional configuration data you need in the system. So usually SRAM batteries only last for, well, a relatively short amount of time, but this can still be like a year or more. But these are also relatively expensive. So FRAM seems to be one of the most promising technologies out there, and it's already available in some devices. So FRAM is great because it just is relatively energy efficient, it's relatively low cost, and so it can have a number of interesting applications. For example, you could use it to log data in portable or even implantable medical devices because of its low energy consumption compared to all the other sorts of non-volatile memories such as EEPROM, and you don't have to take it out to replace it because FRAM has a very high number of write cycles. Similar, you can use it as an event data recorder in automotive systems, so in case of a crash or car failure, you still have a log, you know what was going on before this disaster happened. It's already used in smart meters for energy because it has relatively fast write speeds and high endurance, and you could use it in industrial PLCs. There, it's an ideal replacement for the battery backups SRAM that was usually used there before, and also for EEPROMs that were used to store configuration data. So there is a number of useful applications, and one of the first microcontrollers that actually used FRAM and supplied FRAM on chip was a Texas Instruments microcontroller from the MSP 430 16-bit series, which has the great name of MSP 430 FR 5994. So the FR stands for ferroelectric RAM. So this is a relatively weak, small microcontroller. It's a 16-bit device running at 16 megahertz, but it has 256 kilobytes of FRAM, and in addition, it also has a little bit of SRAM, 8 kilobytes to be precise. So FRAM is ferroelectric non-volatile memory, and it has some very nice properties like a long write endurance without degradation. So you can read and write this FRAM depending on the manufacturer between 10 to the 10, so 10 billions to 10 to the 15, so a trillion cycles. So this is quite a long time. Also, it manages to retain data for a long time without being powered on. So 10 years are guaranteed. For some manufacturers, you even have 50 years. And compared to Flash, you don't need to erase bytes or blocks before, so this is also more energy efficient. And every FRAM write is thus non-volatile because you don't have to erase it first and then rewrite it. Now, if you compare FRAM to static RAMs, which is volatile, then you have a number of trade-offs. So FRAM is usually quite a bit slower, so the access speed is limited to around 8 to 10 megahertz, so usually it's about 100 nanoseconds access speed, whereas SRAM usually can be accessed at the maximum operating frequency of a device. Now, this is not very problematic for a 16 megahertz microcontroller because, the speed difference between FRAM and the CPU is not big. But of course, if you try to run a several hundred megahertz microcontroller, then this microcontroller would have to wait for every FRAM read or write access. And though it's relatively energy efficient, it's still not as energy efficient as SRAM. So if you access FRAM, then it results in a higher power consumption compared to SRAM, but then you have persistent information in your FRAM, which is non-volatile. So what we're doing now is we are going to take a look at three approaches to provide solutions for this intermittent computing problem that have been presented in the literature over the last couple of years. And each of these takes a different approach. And in the end, we'll have a bit of a summary summarizing these three approaches. So you see, this is still a very active research topic, so it might take a couple of years for more robust, more useful tools to appear for this, which are not just academic prototypes, but can also be used for robust industrial products. Nevertheless, since we're talking about the future of IoT also here, I thought it's interesting to show them to you here. So the first project is a project called Ratchet. You see the ratchet on the right-hand side, which is a symbol for what we're taking. So we're running until a certain state, and then we glide back only to the last state we actually managed to click in with our lever at point A here. So it's essentially a gear with these specially formed teeth, which can only run in one direction. But if you try to run it back, you can only run it back so little. So this symbolizes checkpoints. So Ratchet was built out of the idea to provide intermittent computation without additional hardware support or programmer intervention. So prior work that was published either needed specialized hardware or needed the programmer to especially provide checkpointing information. And Ratchet was built to eliminate this requirement, and it does this by extending a compiler to automatically add checkpoints to code between sections, which we call idempotent. And using static analysis methods on the source code of your application, these idempotent sections are identified. Now, Ratchet is a solution that exclusively uses non-volatile memory, so it assumes that all memory in your system is non-volatile. And the question is, does this solve our problem immediately? So if we just run our program on non-volatile memory, everything's fine? Or do we need to do something in addition? Now, Ratchet, the authors actually figured out some checkpointing problems, and some of these we've already discussed before. So the first problem is checkpointing cannot be added to any arbitrary location in a program execution. And the problem that's exhibited here is the so-called write after read problem, which shows in completely non-volatile memory systems. So this means you have a checkpoint which you store at a certain point, and then you execute some instructions after the checkpoint before taking the next one. And these instructions or the effects of these instructions, so the data written to memory, these are not lost because you only have non-volatile memory. So in the application or in this piece of code on the left-hand side, you just copy uh, a variable b to a variable a, but you don't do it directly. You have a and b being pointers to a variable, so you dereference b and you write its value to memory at location a, and then in the next iteration, in the next instruction, you immediately write the value 42 to the memory location of b. So essentially, before the A instruction, you had, something in memory, which is X in A and Y in B. So after executing these lines of code, you have the value of the previous value of B, which was Y in A, and you have overwritten B with a value 42. Now let's assume we start running this code and we have a power failure at the red line here. So first we have what we expect. So we have y in A, so the previous value of B, and then we have 42 in B. But unfortunately, this is non-volatile memory, so these values persist after we power on our machine again. So if we assume that our checkpoint was just before, then we would just continue executing and executing that operation again. But now B has changed already, so the value of B we're reading here is the value of 42 that we wrote in our previous execution of the code before our power failed. So now we have an incorrect value in A, which is problematic. And this is a so-called write after read problem. So you're not supposed to read this value of B again to copy it somewhere else, but you execute this code twice because of the power failure, and so you have a data inconsistency here. So the idea of Ratchet is to identify these idempotent sections, so the sections in the code which can be re-executed and are guaranteed to obtain the same results. And essentially to solve this write after read problem, Ratchet now inserts a checkpoint between the write and the read, so it makes sure that the value of B is still at a consistent value when we have to re-execute the code here from the checkpoint, and then we obtain the correct result. Now, of course, each of these methods we are discussing has some overheads. So obviously we're taking checkpoints. So, when we take checkpoints, it takes time. So, our execution time increases. So we have different algorithms here on the x-axis, like an RSA encryption algorithm, a CRC, a checksum algorithm, a Fourier transform, an SHA crypto algorithm, some image processing, string search, graph processing, and some basic math functions. So you see the behavior differs because there's different amounts of checkpoints that can or need to be taken. And you see for some applications, actually, an execution without intermittent computing support, without Ratchet, actually would fail. So this is indicated by the red fail here. And then you see different configurations of Ratchet with optimizations, which actually reduce the overhead. But you can see that for very many use cases, you have an overhead that's at least a factor of 2 or even higher. But you can apply some optimizations to actually improve this a bit. Now, the other trade-off you have to do when you use such an intermittent computing support system is that your code size increases because you have to add checkpoint calls and recovery code. But as you see on the right-hand side here, this actually increases by a relatively insignificant number. So it's just usually between 1 and 4%. And we even have a case where, and for explaining this, you probably have to read the paper, where the amount of code actually goes down when we insert checkpoints here. That's pretty interesting. We've seen checkpointing as one solution, and we've also seen that another solution is to split our program into small tasks, which are either executed completely, or we have to start them from scratch. So one critique of Ratchet was that it only works on devices that only have non-volatile memory, but many of the shelf microcontrollers, as we've seen in the MSP430, have what we call hybrid memory. So we have an amount of non-volatile memory and also a bit of volatile memory. So the TI microcontroller, the MSP430, had 256 kilobytes of non-volatile memory and 8 kilobytes of SRAM, so volatile memory. The other critique of Ratchet is that actually it has to do a static analysis to find these points, and this is mostly constrained by the amount of effort you can put into analyzing the possible values of pointers in C code, because a pointer in C can point to any memory location. So this does what we call shadowing of variables. So essentially, at one point in time, a pointer could point to variable X, and then the next time it could point to variable Y. And it takes quite some effort to figure this out completely, or you have to go to on the safe side and over approximate the amount of values that, for example, can be changed when a pointer is written to. Now, Alpaca doesn't use checkpointing, but it uses what we call a static task model. So splits an application into tasks, and these tasks manipulate privatized copies of data. So whenever a task starts, it copies the data it needs from non-volatile to volatile memory, and only when it completes and commits the completely changed data, so all the results it obtains back to non-volatile memory in one single step. So this is what we call a transaction semantic. So if power fails during the execution of a task, all its changed data is in volatile memory, so it's thrown away. And if we have enough power to write the checkpoint, then we have another consistent non-volatile state here. So this is very similar to, maybe you know it from database technologies, to the use of transactional memory with redo logging. So in Alpaca, the programmer has to decompose his program or her program into tasks. And then, of course, these tasks need coordination. So you have to explicitly transfer the control flow between these tasks. So you have to split up your program And then you have to actually consider how these small parts of your program have to work together, in which order, and so on. And then you have task shared variables, you have global scope and all the non-volatile state, and then you have task local variables, so your private scope, which is just initialized by the task and which is volatile because we store this in volatile memory. And by just having all the private data of a task in volatile memory, we can guarantee the atomicity of a task. So even though, we execute only part of the task, its results are not seen after we get power again because they were in volatile memory, so they will be erased. So when we start that task from scratch, then it starts at the last consistent state in non-volatile memory. So values here are privatized. That's what the major contribution of Alpaca here is. For example, scalar values, which means a variable is copied to a private buffer, and, uh, and then subsequent accesses are redirected to a private buffer. And the optimization that can be applied here is that only privatized variables are involved in write after read dependencies, so you can actually reduce the amount of data you have to copy. So Alpaca has quite some overhead because you have to do all this copying around. So this is on the one hand, on the left hand side, normalized to plain C. And then when you do some optimization, it is compared to different approaches here. So you have two different approaches, chain and dyno, which are not discussed here. And you compare it to plain C on the left hand side. And you see Alpaca has an overhead between a factor of 2 and a factor of, where are we here? Yeah, a factor of 4, I'd say, yes. Whereas other existing approaches from literature have quite a higher overhead, which you can see on the right-hand side, when all of them run on harvested energy. So for them, it does not make sense to compare against C, because C programs would never run to completion here. And you see Alpaca is quite useful in this concern, because all the other approaches from the literature use much more energy here. Use much more performance here. Now the memory consumption is also reduced in Alpaca because we're not using checkpoints, we're using tasks. So essentially we have low non-volatile memory usage, and this is relatively important because very often the amount of non-volatile memory is relatively low, and alternative solutions can use up to 5 times the amount of non-volatile memory when they have to do elaborate checkpointing, for example. Now, the final solution we want to discuss is called chinchilla, so yet another animal. And chinchilla actually found out that with ratchet and alpaca, it's hard to guarantee the forward progress and eventually the termination, so finishing a program. So with the explicit task model in alpaca, this requires careful programming for non-termination programs, and this makes it in turn hard to estimate the energy used for various task inputs. Whereas for automatic checkpointing in Ratchet actually more or less blindly inserts checkpoints without considering non-termination of programs, and the programmer does not have control over the duration and energy consumption of a certain task or section. And this is a problem that cannot be fixed with such an automatic approach because the programmer doesn't have any influence on the modifications done to his or her program. So Chinchilla had the idea of using adaptive dynamic checkpointing. So we still do dynamic checkpointing, and all the checkpoints that are inserted conservatively to avoid non-termination of the program. So or the other way around, to guarantee progress and eventually termination. But the idea is then if a checkpoint is not really needed, we don't execute it, but we can at runtime dynamically disable a checkpoint to minimize the overhead. And this is done by decomposing the code into very short, predictable blocks, so predictable in terms of energy, with some criteria of being statically defined, that they're relatively frequent, so we always have some checkpoints to work on, that they're easy to measure the energy costs, so that they don't have loops or if conditions or whatever. And the energy variance is also pretty low. And this can be used in basic blocks, so basic blocks are a terminology from compilers. So a basic block is essentially a sequence of machine instructions where it can only jump in at the beginning and it can only leave it at the end. So it's always terminated by a branch or a jump instruction, and you cannot jump somewhere in the middle. So it's a linearly executed sequence of instructions. And of course, you can count these. You always have the same order of instructions following each other, so it makes it easier to do the energy analysis with the inter-instruction effects we've seen in the first energy lecture here. You can also define what they call atomic blocks here using a keyword added to C, which is called atomic, which enables a programmer to actually define these relatively simple blocks on his or her own. And of course, chinchilla also has some overhead, but comparing it to alpaca and ratchet, we see we can have quite some speed up here. So compared to ratchet, we can actually have a 2.25 times speed up because we use very many fewer checkpoints. Even though we inserted them, we only use them sparingly by disabling a large number of them. But compared to alpaca, in a hand-optimized version with tasks, we can only see an average of 2% speed up, but nevertheless, that's better than nothing. And if you look at the code size here, then, Chinchilla has quite a high code size because it inserts a large number of checkpoints, but that doesn't mean that this code is always executed because a large number of these checkpoints are then again dynamically disabled, so jumped over at runtime. So they're in memory, they require non-volatile flash, for example, but they don't necessarily influence your execution time. And if you look at the number of checkpoints taken, you see that alpaca and ratchet actually are very conservative here, and chinchilla, if you look at the actual checkpoints taken, is like orders of magnitude lower because it does this sophisticated analysis. So the selective checkpointing approach presented here has quite a number of advantages, but the disadvantage is simply that it uses much more memory in your code. So this concludes our discussion of energy in the IoT. As always, we're only scraping the surface on some of the topics, and we want to give you an overview, and we want to give you an overview of what's going on. So in this lecture, we talked about intermittent computing, the challenges behind it, how can we ensure progress and correctness of computation in the presence of frequent power failures and restarts. We've seen a bit about non-volatile memory that we can use to store all the important state across power failures, and we've seen two major approaches, checkpointing and the task-based decomposition of code, and subsequent optimizations and iterations on this in different research projects. And then, of course, we discussed the advantages and drawbacks of these different approaches and compared them. So this concludes the technical contents of our course. Thanks for listening. We'll have a final lecture 17, which just summarizes all the important contents of the course. This will be available in a bit. And then we finish this semester after 17 lectures. So thank you for your participation. Thank you for listening and joining in. Until lecture 17. Bye.